In this Foenix Rising recap, we'll cover kernels, and specifically the Foenix F256 kernel. And there are a number of kernels to talk about here. We're recapping issue number 4, which was published in November and December, or published in December, but based on some materials gathered and writings as of November 2022. This is what it looks like. So as always, you can download these from the Foenix Marketplace. Check the description for the link to that site. And this one is, I think, this is 26 pages. I'll just be covering probably 4 pages of this. This is the first of 3 parts, a 3-part series, if you will, covering the F256 platform and various kernels, both that were in development at the time of its kind of prior to production, the released kernel, and some things that are happening right now in terms of kind of re-release or the open sourcing, if that's a verb, of the original OpenKernel that Gads was good enough to invest some additional time in and donate to the community. So we'll talk a bit about that a little bit later. But part 1 is introduction, and I'm going to start with this edition, which has a number of articles all in and around the F256 and the announcement of the K. And I produced one other video, which was based on the first Flash feature, which is issue 5. This is issue 4. So to get right to it, the article on page 3, entitled Kernels, and the Junior Foenix Kernels Explained. What's in the name? Where did it come from? Where did they come from? And what do they want from us? Well, it talks about the origins of kernels, talks about Bell Labs, Unix. There's a couple links in here. If you get the PDF, you can click on the links to see this legendary video, which has, I believe, Ken Thompson and Dennis Ritchie talking about the origins of kernels. And I believe there's some rudimentary animation on the screen. I'll put it up here. That kind of talk over here, actually. That kind of shows layers of a core and various services built around it. Of course, the 1980s systems, 1970s, late 70s, early 80s systems weren't that complex. In fact, the kernel was more of an ABI, or an application binary interface, with a number of calls or vectors, more than an actual kernel that did things like give you memory when you needed it, or arbitrate between a number of servicing processes looking for the same access to the same I/O. While some of those things do exist in some microcomputers, you don't see too much of it in terms of the early days. So let me at least just talk a little bit more about this article, and then we'll get into some Foenix specific items. We'll talk about the re-release of OpenKernel. It was once called OpenKernel, and the GitHub that contains it today. Then we'll talk about something that I'm doing with it personally, just kind of a personal project, which I'll also release once I get further along. So I'll give you a little preview of that as well. So I started talking about this already. I'm going to just move on quickly and just say that there's a history that I recap here on the right column of page 3, which talks about the ROM-based kernels and extensibility, and the fact that in the early days, when a company like Atari or a company like Texas Instruments or a company like Commodore finished the machine, they popped those ROM chips into the sockets in some cases, soldered them directly onto the board in other cases, and put 3 screws or 4 screws in the bottom, put some cello wrap around it, put it in styrofoam, packaged it, and shipped it to Toys R Us, which was a US-based toy store, or a hobby shop, or a computer store. And they were sold by the tens of thousands, and if there was a problem with it, well, what do you do about that? There's no USB updating. There's no way to flash a kernel. These days, of course, things are very different. But in the early days, even the basic language was a little bit problematic as it was developing. And Atari, in fact, had, I think, 2 or 3 versions of BASIC distributed, luckily on cartridge, but it caused some problems. I talk about that a bit here. We talk about AppleSoft. We talk about devices and Commodore and how they were able to kind of take the IEEE 488 peripheral protocol that was developed for the early PET machines and revamp it to make it lower cost. Based on, I don't talk about it here, but there's kind of a legendary story about Jack Tramiel and how frugal he was, and the fact that at one point there was a supply chain issue with IEEE 488 cables and how expensive they were to produce and procure, and he wanted something less expensive. Hence the creation of the IEC Commodore Serial Protocol port. We talk a bit about Wozniak and some of the work that he did and some of the things he did with regard to the floppy system and how he was able to manage that through the kernel that the Apple had. And then it moves on to talk specifically about the Foenix. This part of it talks, I guess, hypothetically that it's called, do you want a piece of this? Well, kernels want what most humans want: peace of mind, material possessions, and to be loved, not necessarily in that order. So in computers, this is clock cycles. It's keeping the house in order. It's negotiating with timing, circuitry, and peripherals. It's all the things you need to keep the system running well, even for a single tasking, single user application or a game. So there's discussion about that here. And then we move on to talk about the Foenix kernels, at least on the F256 platform. Now, I think in this issue, there is a note about, in the table of contents, the F256 announced back page time machine advert. But at the time of this writing, it was announced, but not too much known about it yet, at least not to the general public. Of course, Stephanie was thinking about it and making plans. I'm just going to quickly flip to that, which is here. And this was the kind of a fake ad talking about the old days and the new days. So this was in December. I'm bringing it up only because here she was saying she was shipping in April. The juniors shipped, I believe, in December or January. So a lot of what was written here with regard to the kernels was based on the then best known information. But here we were, and you can see I talked a little bit about models, different kind of memory map examples. And I think I touched on this in a prior video, but the idea is that you can swap in or page in a bank of 8K, and there's 8 banks of 8K on the F256 platform. And depending upon what you're after, you can either turn it on and use it as a basic machine, and this is the model here, which I call model number 2, which is microkernel or OpenKernel with super basic. So you're basically at this layer talking to super basic, typing commands in immediate mode or writing a program that in turn calls the hardware directly or leverages the kernel to talk to the hardware. Another model would be one where you're not necessarily running basic, but there's some number of elements of code that communicate directly with hardware, again, through the kernel or directly. And then finally, there's the no kernel model, which is user code sitting on top of hardware, which is where a lot of developers like to be. And this is giving you access to the full memory map, again, of all the registers and all the capabilities of the platform without worrying about any in-between interfaces. The benefit being you get full access to the full memory map here. But of course, it's at the peril of you having to write all of these routines yourself. So most of this document is about that, the models, and what you get when you get the machine, at least as known in November and December of last year. It talks a bit about microkernel and how it's providing for the first time native support for an IP stack, for slip bridge over Wi-Fi, etc. It talks a little bit about OpenKernel, and I'll get to that in just a minute. But at the time of this writing, it was thought that OpenKernel would be one of 2 kernels shipped with the machine, when in fact the decision was made to go forward with microkernel instead because of its being more mature, more services. But I'm going to move quickly just to mention OpenKernel and what it's all about. OpenKernel is a clean room version of the Commodore ROM-based kernel that accompanied the Commodore 64, and to a large extent the PET and the VIC-20 as well. This is a list of all of the kernel routines. There's 39 of them in the original Commodore kernel, and the ones highlighted in yellow here are ones that I reference in this article. It starts with the most basic call, which is hexadecimal FFD2. A lot of people will know that one if you ever worked on a Commodore system, and that's the routine to print a single character from the accumulator to the screen, to the cursor position, wherever the cursor is on the screen. And this could be known as like a hello world example, but it's hello A because it's a single character. But then I go on to talk a little bit about how to access devices. And in this very brief 15-line program, we talk about a DOS wedge and how you can access various features of Commodore peripherals using a number of these kernel calls with the jump vectors or the JSR vectors, like set logical file logical file name, device and secondary address, set name, which is the name of the actual file that you're open and close, for instance. So that's discussed here. And then we move on to talk about, we interviewed Gadget in this article. So I interviewed Gadget. We talked a lot about kind of her background, influences, where at the time the microkernel was going to live, how much memory it was going to consume. The early days where she was a young child, like we all were at some point, many of us were at some point, when we first got our computers. And in her case, it wasn't Commodore at all. It was a TRS-80 color computer, the Coco, and I think Model 3 or Model 2 and Model 3 with the systems that she had. And to a large extent, the memory management scheme here, this 8x8, is actually based on what the Coco offered. So she's kind of drawing on her experience to kind of suggest and collaborate with Stephanie on coming up with this. Of course, Stephanie did all of the coding for it in the FPGA to make it happen, but it was kind of Gadget's idea to do something that very much modeled what worked very well in those days. Except here we have, I think, 4 lookup tables versus I think just 2, which may be what the Coco had. But anyway, this is a discussion with Gadget, and it's kind of interview style. You can read through this. And then we move on to this retro distraction, which is a kind of a tongue-in-cheek view at Isaac Asimov and how he was a spokesperson for Radio Shack back in those days. And there are so many pictures of him. If you look, do searching across the internet, you'll find a bunch of things, especially on some of the publications that are available on archive.org. And you'll see a lot of things like this, which is probably the back page of a catalog or maybe a computer magazine. And you'll see him, espousing the benefits of this color computer and how awesome it is. And I just kind of put this together with Captain Kirk here, William Shatner, the Shat, selling the VIC-20. And then here, of course, is the computer that Gadget did a lot of her work on. And if you click here, it'll open up kind of a almost a scientific, educational-based journal, which is a discussion about the instruction set of the 6809, how it compares to other instruction sets. It's a very, very nice document. So if you download this, click here, and you'll get a direct link into that document. It may have been published by I think it was a university actually, but I'll link that separately as well in the description. So that's it for the first part of this discussion. I have a couple other things just to show you. This article goes on and talks a bit about binary coded decimal. I'll cover this in another video. There's quite a bit here, including my attempt to write some parts of a kernel, that being an input routine and output routine, and a really rudimentary memory manager, which I'm proud that I didn't get too far on it, because Gadget came by and made my job a lot easier, having to not have to do this on my own. But there's a lot here. You can have a look at it if you would like to download it again. I'll link it to the description, and you can come to your conclusion on how useful or not it is, or interesting or not it is. So that is what I wanted to cover in this part 1 of 3 to talk about kernels. In part 2, I'm going to talk about, just a quick preview, the OpenKernel and what OpenKernel was and what it's kind of morphed into. I'm going to start with a quick introduction of this flipbook. Really, OpenKernel ABI, the fact that Commodore has 39 vectors in their kernel, which, well, the other page with yellow here. And Gadget implemented or coded a fair number of these, but not all of them. Some of these are not very useful, but this type of kernel or ABI does things like manages input-output of a system, and specifically diskette, tape, keyboard, screen, printer, and other, where other can be modem or a user port that just offers the ability to do bit banging for other kind of devices. They typically will also offer access to timers, and sometimes they access memory in some ways or another, memory management, but not really. But you'll see there are some vectors that do things like setting the upper and lower portions of memory, mem bottom, mem top, and others. And layered products that sit on top of it, BASIC being one of them, do pay attention to that. And of course, this was kind of an investment that Commodore made at the time to get to the point where they can see that they'll someday have 128 megs of memory, K of memory, 128K of memory, or 256K of memory, or that there would be this memory expansion that they and third party like CMD would eventually produce. So those functions or vectors weren't really used, but they were kind of, you could see that they were looking to do something bigger and better and support it in a kind of a common way. And, you know, throughout, there's a lot of things in the kernel that, although it's a common jump off point in high memory, they'll link through high byte, low byte to a 2-byte address in low memory that you can patch yourself and make use of if you wanted to do something before you hand it to the official kernel call. We'll cover that another time as well. But I wanted to point out quickly 2 classes of functions or vectors that Commodore always provided access to. One of them are useful, deemed useful, like plot. And the way plot worked was, if you set the carry, you can use it to ask the system, where's the cursor? And it'll return in the X and Y registers the X and Y location of the cursor, which is handy. So you can ask it, set carry, call plot, and save off your X and Y, and then do something like move it to a different location on the screen, print some data, and then jump back to where it was. So that's kind of a useful use of the plot command. And of course, if you clear carry, then it moves to cursor position X and Y. This is one of the useful function calls, and this one's implemented in OpenKernel and also in the newest version of OpenKernel, which I'll get to in a moment. Then there's, of course, the useless functions. One of them is called setTMO, which sets the timeout for the then non-existent IEEE 48 bus. Now, the asterisk here says, seek compute publication mapping the Commodore 64 on page... I don't have it with me. No, I do. I'm going to get it. Here we are. FE21, set timeout flag for the IEEE bus. setTMO. setTMO, yeah. This documented kernel routine can be entered from the jump table at FA2. The routine sets a timeout flag for the IEEE bus. When timeouts are enabled, Commodore 64 will wait for a device for 64 milliseconds, ironically. And if it does not receive a response to its signal, it will issue a timeout error, loading the queue, blah, blah, blah. This routine is for use only with the Commodore IEEE add-on card, which at the time of this writing is not yet available. Great. Not very useful, but this is probably an artifact of the PET IEEE interface, which was the only interface at the time left in here, and I guess it was implemented at some point or not. Of course, Commodore didn't release an IEEE drive for the Commodore and for the 64 until the SFD came out, and they had an accompanying IEEE interface as well. So I assume it was used at that point. But you'll see a mix of this throughout the kernel. You know, some things that are kind of legacy and some things that are very useful. Speaking of which, briefly, I have my notes here, which I'm working on. List of kind of the most useful and the not as useful commands here. And we'll discuss that next time. So that's it for now. Oh, one last thing. OpenFNX kernel or OpenKernel or Foenix kernel, not sure. The name's evolving as I speak here. We haven't settled on it. But it's written by Gadget, and this is, again, clean room, which means if there's something that will print a character on the screen at a given location with a logical cursor managing it, it's really just a matter of having the same calling procedure, meaning that you put a character into the accumulator, you jump or JSR to FFD2, and it returns back once the character is printed on the screen or written to screen memory. But this is what Gadget kind of gave the community, which is a list of a whole pile of these calls. And I'll cover this in detail in the next video, but I've been working on this and studying it and enhancing it across the prior probably 2 or 3 weeks. And I've taken it to the point where I'm almost ready to show it to folks and some of the things that I've done, you know, to suit my own needs. But it's rather lengthy. It does call some of the F256 kernel, microkernel primitives for things like SD card access. But anyway, we'll get to that next time. Hope this has been useful. Please have a look at the description below and forward this along to anybody you think might benefit from some of the background. And we'll see you next video.